So I wanted to talk about the Leetcode daily question for today. It's called maximum count of positive integer and negative integer. And basically, you're given an array nums sorted in non-decreasing order, and you want to count the number of positive integers and the number of negative integers, and return the maximum of those two numbers. And zero does not count as either a positive or a negative. And so I think this is probably one of the easiest questions on LeetCode if you're just doing the brute force. Um, I think most people who know how to code can just do this in their sleep, like just keep track of the number. I mean, the question basically tells you exactly what to do. It's just implementation from there. You keep track of the number of negatives and the number of positives, and you can iterate through nums and say if the number is less than zero, then that's a count for the negative, and if it's greater than zero, that's a count for the positive, and if the number is zero, we don't care, and then we just return the max of those two. And there we go. However, where this problem gets a lot more interesting is the follow-up, where it says, can you solve this problem in O of log n time complexity? So this solution is just the brute force O of n complexity iterating through the entire nums array. Um, but this is asking, can we uh, get more efficient than that? So the fact that they're asking for an O of log n solution and the given nums array is sorted in non-decreasing order, that should set some alarm bells off in your head that this could definitely be binary search. And why would binary search work here is because if if you choose a random number in the middle of nums, because it's sorted in non-decreasing order, you can you can be sure that every number to the left of that number is less than or equal to that number, and every number to the right of that number is greater than or equal to that number. So the first thought might be that we can binary search for the rightmost negative number, so this -1, and then we can guarantee that everything to the left of that is also negative, and that would be our negative count. And then we can take the length of nums and subtract from that to find all the positive numbers. But we actually have to be careful because zeros are neither positive nor negative. So actually, we're going to have to run binary search twice. Uh, once to find the rightmost negative number, and another time to find the leftmost positive number. So I think if you understand binary search, then understanding the concept of how that could help us here is not that difficult, but implementing binary search can definitely be challenging. And I think a lot of times people run into problems with edge cases and off by one errors and time limit exceeded with binary search. So I think I can give a pretty solid structure for how to approach binary search, and that will help you be more consistent in implementing it not just for this problem, but a lot of different binary search problems. So I think getting straight into the code will be helpful for visualizing it. And we'll start with finding the um, number of negatives, right? So basically, the first thing you want to think about in binary search is what am I searching for in the array? And so if we look at example 2, as we said, for the number of negatives, we want to find the rightmost negative number. So that would be this -1. And basically, how are we going to come to that rightmost negative number? Basically, we have to think about what we want to eliminate from contention and what would be a potential solution. So we want to eliminate from contention any number that is 0 or greater, right? Um, and then we'll consider any negative number as a valid potential answer. And then the way I like to do binary search is you want to have a bias for eliminating things from contention. And I'll show you how that works in a second, but basically that allows uh, the algorithm to find positives or zeros or positives more often, and then it can eliminate those from contention and find the rightmost negative. So first, we're going to start with the left pointer at 0 and the uh, right pointer at the length of nums -1. That's pretty standard. That's our potential solution space. And then we're going to have a while loop. This is the standard binary search template. If you don't know it, you can look at other videos on binary search, but this is more for like refining your uh, consistency in binary search. So we have while L is less than R, and so we're going to calculate M, and this is the standard way to do it. I'll talk about what we should do about calculating M in a second, but this is going to get changed. So as I said, we're looking for the rightmost negative, and so we want to eliminate any zeros or positives from contention. So we're going to say if nums M is greater than or equal to 0, then we want to that eliminate that and everything to the right of it from contention. So let's say we landed on this 0. We want R to be shifted um, from wherever it's at to the index before this 0 because this 0 can definitely not be a potential solution. So else, if nums is less than 0, uh, then we know that could be a potential solution. Um, so we're just going to set L is equal to M, basically. Uh, and we're not doing M plus 1 because you don't want to assume the next index is also a valid potential solution. Like if we ended on this, the next index is not valid. So We we always want to just keep track of that. And so the problem now is that we can sometimes get stuck in a loop because this integer division will have a bias for finding smaller numbers. Um, and so it will keep going to the else and stop eliminating things from contention. Um, and you don't want that. You want it to have a bias for eliminating things from contention. So the way a way you can do that is just add a plus one here, and then the algorithm will basically have a bias for uh, greater numbers. And I suggest like definitely writing out the algorithm uh, and like dry running through an example to see how that changes the outcome. But that's kind of the best way I can explain it is that it has a bias for larger values, and we once we find those values when they're not valid, we can eliminate them from contention. And so after this algorithm, our solution for our target of what we're trying to find is going to be L. Well, that will be the index of our target. So since L is the index of our target, so this would be index 2, uh, we know that this number and everything before it is negatives. So basically our negative answer can be uh, L plus 1, right? Now, there's one edge case that I'm missing here, and that is in example 3. If all of the numbers are positive, then actually we have a problem. And you might have spotted it, but basically it's that in our starting solution space, L is starting at 0. So basically the smallest index in our solution space is 0. And so even when there's all positives in this example, uh, the binary search would return 0 as the target when that's not our leftmost uh, or sorry, rightmost negative. There's actually no negatives. So basically we have to add -1 as a potential solution to the solution space. And then so this binary search on this would return -1 for L, and then plus 1, the number of negatives would be 0. So that fixes that edge case. And now once I've once I've explained finding the number of negatives, finding the number of positives should be pretty easy. Now, firstly, you have to keep track or be aware of the other side of the edge case where it could be all negatives. So basically, you want your solution space can still include 0 here, but then you want your right side solution space to include the actual len nums, which is outside of the indices. And that would allow you to find a uh, rightmost negative index that is out of bounds. So after you've done that, you can get into the next binary search where you are looking for the leftmost positive number. So in this example, that would be 1. Uh, and so when you're looking for M, you can actually have a bias for smaller numbers now because the smaller numbers are what you want to eliminate out of contention, right? So you want to check if the number is less than or equal to zero, then you're going to eliminate that from contention by doing by shifting L all the way to M and then the next. And then else you're going to do R equals M because if nums is less than zero, that's a potential solution, right? I mean, greater than zero. If nums is greater than zero, then that's a potential solution because we're finding positives. So then the solution returned from this would be at R, right? Because these are our potential solutions. So once you have R, um, positive is going to be the length of nums minus R, right? And so we can test that, right? Our leftmost positive here is 1. That's at index 0, 1, 2, 3, 4, 5. That's at index 5. And then the length of nums is 7. So 7 minus 5 is 2. There's two positives in this. So that is our binary search technique of finding both negative and positive. And then we just return the max of negative and positive. And that should be a correct solution. And there we go. We beat 100%. So I think this problem is pretty interesting once you get into the binary search aspect of it. And I think it's a really great way to understand binary search concepts a little bit more deeply because I think a lot of people understand binary search and know how to implement it a little bit, but I think having a structure of how to think about it and thinking about, okay, what am I searching for? What am I trying to eliminate from contention? And also thinking of edge cases in the solution space. I think those are all things that make binary search a lot more difficult. And I think getting practice with that so you can be more consistent and not keep getting TLEs and off by one errors in binary search is really good practice.